plus ut. So ut is a zero mean stationary process, so mu is the mean of z. Okay, but in the real world, of course, it may be important to allow for time trends in addition to a constant, so that distinction could be important. Okay, so the theory of co-integration can be extended to other specifications of the deterministic variables. So for example, the linear combination of x1 and x2, it may be stationary but around a deterministic linear trend. Okay? So in the general case, if x1 and x2, now we know that they are I1, so they must definitely have a stochastic trend, but they could also have a deterministic trend in addition to a stochastic trend. And to model this case, we can add a deterministic trend term to the equation. So in the regression formulation now, x1 is mu plus mu1t plus beta 2 x2 plus ut. So that if we look at the linear combination now, then this linear combination is no longer stationary, rather it is stationary around this deterministic time trend. Okay, so we distinguish between these cases so x1, x2, they have both a deterministic trend and a stochastic trend. Then we have two cases here. One is so this case, we say we have stochastic co-integration. And if we have this, then we say we have stochastic co-integration plus the deterministic co-integration restriction. Okay, so what that means, so here in the first case, the co-integration vector eliminates the stochastic trend when you form the linear combination. Okay, the co-integration vector eliminates the stochastic trend in x1 and x2. That's what we normally mean by co-integration. But here, the co-integration vector not only eliminates the stochastic trend in x1 and x2, it also eliminates the deterministic trend. Okay, it also eliminates the deterministic trend. So here, not only do we have stochastic co-integration, but the deterministic co-integration restriction is also satisfied. So the same co-integration vector which eliminates the stochastic trend also eliminates the deterministic trend. Okay? And when when we are testing which one to test for, well, that depends on the economic model. Okay? If the economic models typically typically will be of which form? Form 1 or form 2? Most of the time. Form 2. Okay? Most of the time, economic models will tell us the relationship between different economic variables. They will say, well, yeah, the long-term rate depends on the short-term rate. They will not say the long-term rate depends on the short-term rate plus a time trend. Okay? Time trend is not really an economic variable. Okay? So most of the time, we should test for this. That's what the economic model implies. Okay? But there is room to play around. If you don't get co-integration with this, then people will cheat a little bit because you want to get a positive result, right? You're trying to prove that this is related to that. And if you don't get success this way, you try add a time trend and see if that works. Then you have some kind of support for the theory. It may not be very strong support, but this definitely is stronger support for the theory. If the theory implies an equation of this form, the theory is really saying that the same co-integration vector has to eliminate the deterministic trend as well. Okay, so now we talked about the idea of co-integration, and we mentioned that we think of co-integration as an equilibrium concept because the individual I1 variables are wandering around, they could go anywhere, but the linear combination is stationary. It can't fluctuate too much. It is stationary. So then the question arises, well, what is the force which keeps the linear combinationary? So what is the source for sustaining the underlying equilibrium? Okay, can we understand the logic behind this? Okay, so x1 and x2 are co-integrated, then beta prime xt, that's going to be stationary. Interpret the relationship as defining a long-run equilibrium between x1 and x2. Now, logically, for an equilibrium to exist, there should be some force in the underlying model, in the underlying data generating process that enforces the equilibrium, okay? And that ensures that these non-stationary variables, x1 and x2, they do not wander too far away from the equilibrium. So two econometricians, Engel and Granger, who came up with the concept of co-integration, they showed a famous theorem, and this is known as the co-integration representation theorem, according to which x1 and x2 are co-integrated if and only if there is an error correction model for either x1 or x2 or both. Okay, so there should be some underlying dynamic mechanism which pushes you towards this equilibrium. Otherwise, there is no equilibrium without such an error correction method. So error means that you are away from the equilibrium. Error correction means that you go back, you're pushed back towards the equilibrium. So there has to be, if x1 and x2 are co-integrated, there has to be some error correction mechanism, okay? And they proved formally that this error correction mechanism always exists. So they are co-integrated if and only if. And Nobel Prize for their work on error correction, okay? So co-integration and error correction, very important contribution. So let's try to understand this.
时间序列，为什么没有这个mu乘以 t？ 为什么还是去参与模型？这样我刚刚觉得他写字幕头上，去再听一下。
Okay, so we start with two variables that are I1 and they are co-integrated. So we can have this regression interpretation of this, and because they are co-integrated, that means ut, the residual, has to be stationary. Okay, the residual has to be a stationary process. That's the very definition of co-integration. So they are co-integrated with this co-integration vector 1 minus beta 2, and so this deviation from equilibrium is stationary. Now, in the first lecture, I told you an important result. Any stationary process has the famous theorem, Wall's decomposition theorem, right? When we defined the idea, the concept of stationarity, we said any stationary process has what kind of representation? ARMA, right? So it has an ARMA representation. Okay, so now we use this result. Ut is stationary by definition because x1, x2 are co-integrated. So ut is stationary, so ut must have an ARMA representation. So ut has an ARMA representation. Now, it could be any ARMA process, but we, for simplicity, assume an AR1, okay, simplest possible case. So we write ut as theta ut minus 1 plus epsilon t, where theta is smaller than 1. Okay? It could be any ARMA process, okay, but the logic is easiest to understand with a simple one. So let's do it for a simple one. Now, we're going to replace ut with this. Okay? So ut is x1t minus mu minus beta 2xt. So I'm going to replace this. I'm going to insert this part. So on the left-hand side, x1t minus mu minus beta 2 x2t, that is ut, equals theta x1 t minus 1 minus mu minus beta 2 x2 t minus 1. So lag value plus the error term. Okay. Now, so I'm just going to move this whole thing to the right-hand side. So I keep x1t, and then mu plus beta 2 x2t and everything else is the same as before. Okay, now I'm going to play a small trick. So I have here plus theta. I'm gonna write this as minus 1 minus theta. Okay? And the inside part is the same as before. Okay, so basically this plus theta I still have, minus of minus theta, that's the same as before. The extra thing here is the minus 1. So I've subtracted this term, right? So what I'm going to do is add it back. Okay, so I'm basically adding and subtracting this term in the brackets. So that doesn't affect the equation. Is it clear? This is the only tricky step. If this is clear, then everything will be clear. Is this okay? Okay, good. So now I can cancel this mu with minus mu over here. Okay? Then this x1t minus 1, I'm going to bring it to the left-hand side. So then I have this on the left-hand side. And then I'm going to combine these two together. So then I have beta 2 times x2t minus x2t minus 1 minus 1 minus theta, and the same thing as before. Is this clear? So now the left-hand side is delta x1t. It is the change in x1, right? From time t minus 1 to time t, delta x1t. On the right-hand side, I have beta 2 times delta x2t. That is the change in x2 from time t minus 1 to time t. And then 1 minus theta x1t minus 1 minus mu minus beta 2 x2t minus 1 plus epsilon t. This is called the error correction model. And let us see why. Well, this term in the brackets is the error at time t minus 1. So this is the error from the last period, right? If the economy is in equilibrium, then x1 will be exactly mu plus beta 2 x2. Right? If it is not, that means there is a deviation, there is an error. So that is the error at time t minus 1, the deviation from the equilibrium. Okay? Deviation from the equilibrium. Now, what are we saying over here? This is the change in x1 today. Okay? So, now what do we know about this 1 minus theta? Is this going to be positive or negative? 1 minus theta is going to be positive. Theta is smaller than 1 in absolute value. So we know that 1 minus theta is positive, so minus of 1 minus theta is going to be negative. Now, what does that tell us? That if this error is positive, if in the last period the error term is positive, that tells us that x1 is relatively too high or low compared to its equilibrium value. If the error term last period is positive, that means x. Now, if we were at equilibrium, then this error should be 0. If this error is positive, that means x1 is too high compared to its equilibrium value. The error is positive. If the error is positive, this negative number ensures that the change in x1 is negative. x1 is too high, it needs to go down. Okay? So this negative coefficient ensures that there is an error correction happening for x1 when this error term, when x1 is too high compared to its equilibrium value. That's why this is called an error correction model. Okay? And here we derive this error correction model for the simple case of AR1, but Engel and Granger show in their paper, no matter what kind of stationary process you have for UT, you can always find some error correction representation if x1 and x2 are co-integrated. Okay? So they show that for all possible stationary processes. Okay? So okay, so I did it for the AR1 case, and here it's worked out for the AR2 case. Okay, not much difference between the two. Instead of 1 minus theta, we are now going to have 1 minus theta 1 minus theta 2, and we have a couple of extra terms. Okay, so if you want, you can go through the algebra. But basically, it's the same kind of thing. Okay, so for us, we have this term and this term, and we have the error correction term, that's the same. But they also have these extra lagged first differences. That's the only change. Okay? Now one important thing to note in the error correction model, okay, Well, x1 has a unit root, but the first difference of x1 is I0. So this is stationary. The change in x1 is stationary. Change in x2 is also stationary. Okay? So the only way, so we have something stationary here, we have something stationary here. Epsilon is white noise, so definitely stationary. The only thing left is this. The only way for this equation to balance is if this is also stationary, and that means x1 and x2 are co-integrated. Okay? So co-integration and error correction, one and the same thing. Okay? So notice that under the maintained assumptions, these first difference terms, they are all stationary. And since x1 and x2 are I1, this equation in 5 is balanced in terms of the order of integration only if this combination is stationary. Okay? That is, if the variables co-integrate. If the variables do not co-integrate, if there is no co-integration, the only way to balance the equation is that there's no co-integration, and the only way to balance the equation is to exclude this term from the regression, because otherwise this term would be I1, and these are all in first differences, they are all I0. Okay, so if the variables do not co-integrate, the only way to balance the equation is to exclude this levels term from the equation by setting this parameter to 0. Okay, now we can, now here we are kind of assuming that the error correction takes place on x1. x1 corrects. If x1 is too high, and this coefficient being negative, it forces x1 to go down. Okay? But in general, it is possible for both of them to correct. So from the representation theorem, we do not know whether x1 will correct or x2 will correct or both of them. So it is possible to write two error correction equations, one for x1, one for x2. And generally, we can stack them together as well. So here we have an error correction model for x1, similar to what we derived. And now we write the coefficient of the error correction term is alpha 1. And in addition, we have some lags. Okay? Same thing here for x2. We have the error from the last period. Its coefficient is alpha 2. And then there are some other lagged differences of x1 and x2. So if we stack them together vertically, we get what is called a vector error correction model. So the change in xt, which now includes x1 and x2, is delta plus this matrix gamma times the lags of x1 and x2 plus alpha times the error term from last period plus this white noise process. So what is common to both? This error correction term is common to both of them. Now, how to interpret this alpha 1 and alpha 2? Okay, so if x1 is doing the error correction, then this alpha 1 needs to be less than 0, as we just saw. Right? So that means if x1 is above its equilibrium value, the error is positive last period, a negative alpha ensures that the change in x1 is negative. So x1 declines today, and x1 is doing the adjustment, the error correction.